Should start. I'll just close the door. Oops. Great. Welcome to Advanced Cognitive Modeling. It's nice to see some known faces. Yes, I don't think I've taught your cohort fully, right? Not at the bachelor. Good. Okay, so this is not going to be too much of a repetition. This is me most of the time when I'm not at university. My kids are a bit older. You'll meet them next week because it's winter holidays. So they're home from school. But I was trained in something that's completely different from cognitive modeling. I was trained as a semiotician, which is some kind of humanist that worries about how do we make sense of the world as humans. And I was very intrigued in the question of how we make sense together, right? How our perceptions are imbued by the way that other people interact with us, how most of the decisions that we make are made with other people. And these kind of worries and concerns actually have carried over to what I'm doing today when I identify as a cognitive scientist. At least I've persuaded Aarhus University that they should hire me as a cognitive scientist. And I spend most of my day, when I get to do that, doing computational and statistical models in front of a computer, sometimes even with experimental data, right? Though a lot of my work is on observational data on language development, where you cannot really manipulate kids too much. How do I combine these two things? Well, so the idea that will shine through even in this rather technical course is that the way I see cognition is not as a spreading of neural activations and neurotransmitter processes in the brain, but it is actually a process of meaning making that we do in collective situations. And this is where I had to develop the computational skills that I gonna try to develop together with you during the course, because as soon as we start analyzing individuals and interactions, all the data is a mess, right? The way I behave is changed by the way you behave, which changes the way I behave, and so on and so forth. And in order to model these things, we cannot rely on traditional statistics. Well, people do, but it's crap. We cannot really use traditional statistical tools. The second is that as I started working on these computational models of how the mind and social interactions work, I actually started seeing that these models that people started using, from reinforcement learning that we'll see, to signal detection theory, to drift diffusion models, and so on and so forth, are actually cultural and semiotic artifacts. They're tools that we build to change the way we think. And the way that we use these tools is often very embedded in social and cultural practices. So for instance, if you go to most of the computational or cognitive neuroscience labs that do computational modeling, right, you see that they're all excited about drift diffusion models and reinforcement learning. And they all use pre-made packages. Well, not the MyCast lab, but they all use pre-made packages which forces choices on how to model things. And so even statistical practices, even computational modeling practices are actually social practices with traditions and blind spots. And if we become aware of these things, actually we become better modeler. And this applies also to science, right? The way that we produce science is deeply embedded in tradition, the way that we do things here in this lab. And being aware of these is super important. Okay, So this is me. I'm a former humanist who does lots of computer stuff, trying to keep that perspective, but I really prefer playing with a computer than doing other stuff. Uh, and I'll try to show you how we can combine these perspectives. I also want to hear your names. I'm not going to remember them the first time. And if you want, if you have some specific expectations about the course, also in the light of decision making, which is supposed to be quite coordinated with that. And then we'll start there. Yeah. Good. Yes. Cool. Well, let's finish the table. Yes. Yeah. This is the right course then. Yes. Mhm. Yes. Cool. Yes. Yes. Cool. Yes. Let's take that tape. Yes. That's also we'll do. Stan is getting better. So every year I have to find more messy examples because the examples from the previous years now work. But yes. Yes. Good to go. Yes. Are you the one TAing social and cultural dynamics? Okay. Yeah. Nice. Mm-hmm. Yep. Cool. Yes. We'll do a lot of that. I also have a talk on prior specifically in on YouTube. I think it's called Standing on the Shoulders of Normally Sized People. Yeah. So that's also, I think that's my go-to. That's where I try to cram everything. Yeah. Cool. Yeah. Mm-hmm. Yep. Good. We actually take our time to go through everything step by step. Some of the models will feel simple because we want to build like everything in a systematic way, bringing it all together, right? So that's, but please give feedback as we go along if that's not the case. Yes. Mm-hmm. Yes. Mm-hmm. Mm-hmm. That's cool. Cool. Hmm. Yeah. Hmm. Which you know a lot about. Yes. Last table. Hmm. Yes. Cool. Thanks. This is actually helpful for me. Yes. So what we're going to do now is we're actually going to go into the deep end and we're going to be talking about the pizza problem. We're going to be starting from a problem, and then we will build step by step a computational model that helps us solving these problems. And these examples will be our entryway into what cognitive modeling is. It's not a cognitive example, and we'll discuss why later. So the idea is that if you want to make proper pizza, you need to have an oven that's at least 400 Celsius degrees. Otherwise, the pizza is not good enough. That's a truth. That's a fact. Uh, therefore, you know, crazy people buy dedicated pizza ovens that reach the temperature that your home oven doesn't reach, right? And infrared temperature or thermometers that allow you to accurately measure the temperature as the oven gets, more and more hot. However, if you have kids, they're not going to allow you to stand in front of your pizza oven very eagerly measuring the temperature, right? They need to play. You cannot really see it here. Maybe I should turn off this one. And so my problem, no, too much. My problem is how long will it take for the oven to reach 400 degrees in a precise way, right? Because we want to make good pizza. So take a couple of minutes with somebody at your side. Imagine that you have a pizza oven like that, and you have infrared thermometer. How would you figure out how long it takes for the oven to reach 400 degrees without being able to stand in front of the oven and measure it as it gets there? Okay. So I forgot to bring my own colors. I'll do that in the break, but let's start with some ideas. Has anybody figure out a strategy to do that? Yes? Yes? Good. So this is the answer for somebody from somebody who already took the course, right? So this is how we go in a cognitive modeling fashion is we try to define the equation that underlies whatever phenomenon we want to uh, describe, predict, understand. And we identify which parts of those equations we can know already from previous literature or from logic, and which ones we still have to define, right? Good. Anybody else had other ideas? Yes? Yep. And okay, yeah. So this would be like a traditional statistical approach is we know lines, we know regressions. Therefore, what we're going to do is we're going to measure a few times, maybe make it into a game for the kids so they're with for a while. And then we extrapolate from the curve that the measurements are drawing into the full curve and then use it to predict how long it takes. Yes, these are kind of the approaches that we're going to see, right? So the first thing is we need some data, right? So what we can do is we can use the infrared thermometer, the two kids, and the dad to measure the temperature at more or less regular intervals. So you can see on the top panel that there's three raters in different colors. There's a certain amount of measurements. Not all these measurements are present for all the raters. And the measurements for at least two of the raters, they describe kind of a regular curve, right? While for the third rater, right, you see a lot of noise there. Of course, as we measure things more or less regularly, but in three people, the measurements are not fully regular. So I can replot the very same data down here, just in terms of seconds from turning on the oven, right? Not measurements, but seconds. Every year I look at this data and I think that I could teach a whole course on this because how do we deal with missing data, nonlinearity, repeated measures, intercoder reliability, measurement error. That's super interesting, even if we don't count like measuring how well the pizza came out. But let's first look at what we can do with these data and our traditional tools. So some sort of regression model. Actually, we've done that. So here we take one model, the linear model, right? That draws lines, straight lines. And we see how well it fits the data, separating the measurements by rater. And we can see here is the linear model for N, here is the linear model for R, and here is the linear model fitted on the data from T. I hope that you've been trained so to say that this is crap, right? The linear model is not describing the data well. Why? Yes, Martin? because the measurements that we have here are not linear, right? They're not, yes. You had something else?
Yeah, at least they only do that within a range of the data.
Yes. Yeah. So another thing that you've been taught to do is log transformations. And I hope you're very critical of log transformations, but we can use that and model these data according to a log normal, right? And that's the pink fit. So anybody wants to comment on whether the pink fit is better or worse? Yes.
It seems worse to me.
Yes. Why? Yes. And also, like, so it's assuming that the growth in, yeah, please.
Globally, all of the data points, right? Same.
No, it's actually how did I do? Oh, it's done as a multi-level model. So yeah, each of the three raters contributes to the population level estimate. And we'll discuss multi-level models. So if you don't remember all the details, that's fine. But it just means that we model at the same time the individuals using a specific curve and the population using an underlying curve. And here I plotted the underline, the population level curve, I think. Yeah. Yeah, that's the one that fits best. But it is the population level. So the data have been pooled together across participants. And as Martin was saying, the crazy thing is that it's a spect, even if we know that the temperature of the flame might be, let's say, 600 degrees, it expects the temperature of the oven to keep growing exponentially, right? And that's physically impossible. Now, we could imagine some other transformation, right? And that's usually what people who do in statistical courses. But we can also take the other option that, remind me of your name, Peter? Yes, that Peter was suggesting. That's actually what about trying to infer the equation that's generating the data, right? And we're in luck because physics has done a pretty good job at describing temperature, right? So there's the heat or diffusion equation by Joseph Fourier, which describes how heat spreads in a body, where P at the start there is the density of the solid, the baking stone. C underscore P is the specific heat capacity of the material, how much heat it can absorb. T is the temperature, the big T on the other side, and on top, actually, I should specify that this is a differential equation. How well do you remember your differential equations from high school? So it's basically an attempt to say, what's the change in temperature given an infinitesimal change in time, a very small step. And I really want my colors, Dan. But the idea is that we want to draw continuous curves of how heat is changing in the oven. And that is saying here we're describing the relation between these different variables, assuming that we can look at them at infinitesimal intervals, right, in a continuous fashion. So T, change in temperature over an infinitesimal change in time. Big T is the temperature, small t is the time. K is the thermal conductivity of the material. At that point, I start crying because I don't want to be a material engineer, right? I'm trying to do a cognitive model, or in this case, like a basic model. And I can't even, delta square is the Laplacian operator that represents the spatial distribution of the temperature, because according to the shape of the baking stone and where the flame is touching the baking stone, you might have different diffusion patterns, right? And I like Christian's face because it's really where we are like, is this really what we need to do this? Right. And then Q. Well, the point is exactly, we often meet these very complex models. But what I want us to always think critically is, do we really need it all, right? Both for our mental sanity, but also because starting with very complex model is the key to fail, right? We always want to start with simpler model and build up to complex. So what do? We take a page from the physicist and we say, in joke, but the pizza stone is a spherical cow. You know the joke about physicists, right? Uh, so we actually can simplify a lot of the equation by making a simple assumption. That is, the baking stone, which is not that big, has the same temperature all over its volume. If we can make these assumptions, we can actually use Newton's law of cooling or the lump capacitance model, which is much simpler, right? So we have that a change in temperature over an infinitesimal change of time is given by T, which is the temperature of the stone at this point, small t, which is the time, which we can measure in seconds or in minutes, whatever, H, which is the heat transfer coefficient, defined as watts over square meters times Kelvin, blah, blah, blah. We don't care. We just have one variable. That's how efficiently the heat is transferred between the flame and the material. We have A, which is the surface area exposed to the heat. And I hope that Christian has the same flabbergasted face. Because again, we're going into a lot of details. And this is the point. We're trying to simplify. We're still getting a certain amount of complexity, and I'm going to give you an example of how we can simplify it further. But M is the mass of the stone. C, P is the specific heat capacity, right? It's a simpler model, but still we have a lot of stuff. T with a small infinite is the flame temperature. So how do we go at simplifying these things? We can look at the variables, and we can see that some of these variables are going to change at every measurement. The time, the stone temperature, right? Other variables are constant, right? The mass of the stone is not going to change throughout us making pizza, unless you're really bad at making pizza. It's not even going to change from time to time that we make pizza. It's just one thing. The surface area exposed to the heat, that's exactly the same, right? The heat transfer coefficient, it's also exactly a constant. It's not something that's going to, well, technically it would change as the temperature in the stone is growing, but the effects are not that big, and we can actually keep it, consider it as a constant. So what we can do is we can take these constant variables and make them into one variable, right? So we can say that H times A divided M times CP are all things that are not going to change from time to time that we measure the temperature. And we're just going to lump them into a constant called hot, which determines how quickly the stone heats up. Why are we doing this? Because as Peter was saying before, right, there are some things that some variables that we need to estimate from our measurements, right? And we could do these sort of things, but we don't care, right? What we want is simply to be able to calculate the change in temperature over time so that we can know how long we can play cards with the kids until the pizza oven is ready, right? So we can just lump it all together, which means that that equation can become this. The change of temperature over the change of time is equal hot times now I just don't want to get it wrong, but we call it the flame temperature minus the temperature of the stone. What is this equation telling us? Is that the difference in heat between the stone and the flame determines how much the temperature is going to increase, mediated by the physical properties of the oven, right? Because if there is a big difference, there is more heat transfer. If there is a small difference, it's not going to change. If they're exactly the same temperature, there's not going to be a change in temperature, right? This captures that idea, and that should capture the fast increase in temperature and the slowdown that we have seen in the measurement data. Then we want to solve it because we need to estimate hot. Right? We don't know it in advance. We might want to use it when we go to somebody else's house and make pizza at their house. Right? So we rearrange so that all the temperatures are on one side and the rest is on the other side. We then need to get rid of the d's, right? The infinitesimal changes. We want to get rid of the differential equation in a sense. And from what you remember, maybe vaguely from high school, the opposite of derivatives are exactly, yes. So these s here, right? We put the s in front of the left side. We put the s in front of the right side. Why am I not putting it before hot? Yes. Because you can extract constants that are multiplied by the unknown variables and take them out of the integrals. You don't need to, we're not gonna need to integrate equations in this course, right? I just want to show you what the process is. And it was super fun to calculate it. I didn't remember it either. I had to look it up. So the left side integrates to minus the logarithm of the temperature of the flame minus T. And that's just one of the rules for integrating. I just looked it up. Oops. The right side becomes hot, which was outside, times the integrated delta T, which is T plus a constant. Right? So that's the equation. And then we can determine C by assuming that T at start is 0. Right? If we start from 0, we can then say, sorry, not T. So we start before we start heating the oven. The time is 0. The temperature is equal to the initial temperature. And C becomes minus the logarithm of temperature of the flame minus the initial temperature in absolute terms. So we substitute C with these small equation, and we solve for T so we can have the equation. I'm not going to go through the whole thing, but basically we get an equation for T. That if we know the temperature of the flame, the initial temperature, we already know the temperature of the flame, and hot, and how much time has gone from the beginning, we can calculate the temperature at that point. Now, does anybody of you has an intuition of how we estimate hot, how we figure out hot from this equation? Yes?
We also talked about it in our group at the very start, but like just taking a lot of samples, but knowing the sample rate, so to say, and
Yes.
estimating out of mean.
You don't need the mean, actually. You have here an equation. If you take a lot of measurements, you actually have all the other variables but hot, which means that we can estimate hot from these measurements. Does that make sense? Right. So we have an equation in which there is only one unknown. Yeah, exactly. Because when we measure at time t, right, we can say, oh, right, at time t, the temperature is this. The temperature of the flame that we know is more or less constant. We can measure it at the beginning. The initial temperature we know. Temperature of the flame we know. Hot we don't know yet, but T is the time that went between this and the initial temperature. Right? So we have everything but hot. And that means we can estimate it. Right? So the difficult part so far had been in finding the formal connections between different measurable and unmeasurable aspects of the phenomenon that we wanted. And this is going to be the big challenge in cognitive models, right? So we can measure something, reaction times, stimuli, and we need to define the underlying algorithm that generates those data from some unknown parameters like working memory, right? Executive function, et cetera, et cetera, et cetera. So what we can do next, oh, actually, so I was solving this and then I started second guessing myself. And then I had to use my secret, which is not ChatGPT, but it's my mom, who's a retired math teacher. So I sent her the slide, and then she sent me a picture of her integration of things, and that was working. Yes. Okay. So before we go and estimate, what I always do, and you'll see that again and again throughout the course, is I take the equation, I plug in different values, and I plot it. Actually, these days that I can use generative AI, I usually make it into an interactive plot where I can slide the parameter values and look at things as they evolve in real time. We'll do a bit of that. And I say now that we have generative AI, it's because I've never learned how to do interactive plots. So that's where I'm using it. But we can see here that with very low values of hot, we get that the initial temperature is making a big difference or a relative difference. And we can see that there is not so fast an initial change and then not so much of a slowdown later on. But if we have a bigger heat transfer capacity in the pizza oven, what we can see is that actually there is a bigger increase at the beginning and a faster slowdown, which is what we were seeing in the data. If we increase hot again, what we see is something that's pretty implausible for the data, right? That very quickly it reaches the saturated capacity, the temperature of the flame. And that already gives us an idea of where hot should lie, right? It's somewhere between 0.001 and maybe 0.00678, something like that, but not 0.002. Okay, now what? We can easily measure T at different times. Ti is the initial temperature, and T infinite is the flame temperature. And we want to calculate hot. So we take the equation, we solve for hot, and then we do stan. And this is a sneak peek. I'm going to teach you stan very slowly. Right? We're going to go through all the steps. Now I just want to give you a very first introduction to the whole process that we're going to do throughout the course, right? But here we have the data that we can feed the model, how many data points there are, how many times. So what's the time at which we are doing the measurements? What's the temperature in each of the measurements? what's the initial temperature, and what's the flame temperature. This is the stuff we know. There's also stuff we don't know. One is the hot parameter. The second, which we haven't talked about, is a very important parameter in most of the models that we're going to deal with, which is the sigma parameter. What is the sigma parameter? Think about in a normal distribution. What is the sigma parameter? Yes, it's the variance. Why do we need variance in these models? Somebody new? Yes. Yes.
Outside temperature, which the oven is placed, all sorts of stuff.
Yeah. Yes. So my dad used to do physics research before he became a high school teacher, and he has his papers where you have these data points that line up precisely with the curve. Then they have a bump, and then they go straight. And I remember going to him and saying, "What was going on there?" When he was like, "Well, I was manually cutting the silicone wafers that they were uh, like cooking or baking at different temperature. And after a while, you do that, your arm gets really tired. And that's where the bump comes up. When we deal with humans, like we have to, the sources of error are many more. The data is not going to be following exactly our model. This is both practically, right? We've seen Tristan, but also conceptually. We cannot expect our models to describe everything in the world. So sigma is one of the parameters that allows us to account for deviation of the data from our model. Then we have the model, which basically we're saying there is a vector, right, of temperatures that underlies the measurements. So we call it mu, right? Mean. It's if we were to measure it a bunch of time, supposedly that would be the mean, which is given exactly by the equation that we defined before. Then we say that we have a prior on hot, because Bayesian models, as we will see, always, always, always require a prior for the stuff we don't know. And we say it's a normal distribution starting at 0.005 with a standard deviation of 0.005, right? That brings us from 0, which we cap at 0, right? To, if we want to be generous, 3 times the standard deviation. So to about 0.002, which we've seen was not the ideal one, right? But it's kind of a ceiling. Then we have a prior for sigma, and we put an exponential, so it starts at 0 because we cannot have a negative variance. And it has a long tail, so we allow for the model to have big errors when modeling the data because we've seen Tristan's measurements, right? And then we have the model that the temperature as measured follows a normal distribution where the mean is the mu, the deterministic result of our model, and a certain variance because there's error. Right? Does that make sense? Again, I don't want you to get stuck on what the heck is target plus and that sort of things, but just getting the idea. We have some data, we have some parameters we want to estimate, and we have a model which is made of the equation plus the priors. Yes. Okay, yeah. So the traditional way of specifying this would have been that hot is distributed tilde as a normal distribution with a mean and a standard deviation. There are reasons for which we're using target, which I'll explain when we cover samplers. It doesn't make any difference in terms of the underlying algorithm, but it makes a conceptual difference. I gotta spoil it. So what the heck? Let's live a little. The idea is that I don't know if you've done it in Bayesian statistics in methods 4, but the algorithm underlying our ability to fit these models is, in our case, is going to be a Hamiltonian Monte Carlo. Huh? Yeah, it's nuts. It's nuts too. Yes. But basically is, how can I explain it at this point in the course? But the idea is that we start in some random place where we say that the two things we're estimating, hot is 0.005 and sigma is 1, right? Then we say, okay, if these were the values, first of all, how likely are they given the priors, right? So we say, how likely is a hot of 0.005 given these prior? And we get a certain number. We then add to that, how likely is a sigma of 1? And that's where we're saying there's a target. So we keep on adding. And then we say, but we also can feed these two values. Well, we fit hot here. And we get an estimated mu. We put sigma here, mu here. How likely is the temperature that we measured, given that we expect a sigma of 1 and a mu of whatever it is, 200 degrees, and these two to be connected by a normal distribution, right? So if the temperature is 400, that's not very likely, right? If the temperature is 250, and that was what the mu is, it's very likely, right? And we add that number to the other two. At this point, we know the log posterior probability, how good those two values for hot and sigma are, given the data and the priors and the model form, the formula. Then we can take a jump in one direction, and then we can recalculate it, right? So now sigma is 1.1 and hot is 0.006. And we can redo the whole thing. We can see whether the log posterior likelihood, the way in which the model fits the data given these two parameter values, has improved, stayed the same, or changed. And then we say, okay, let's say that it's improved. It means we're going downhill, and it's going to carry us in that direction. If it has gone worse, right, then we're sort of going uphill, and probably our movement is going to deviate according to that, right? And so the reason for which we're saying target is to remember that at each of these steps, we need to add all the things in which there is target to assess the log posterior probability. Does that make sense, Martin? Yes. Okay, good. Actually, let's take a break now. Let's take a 10 minutes break. Good. Okay. So how confused are you so far? Okay. So confusion is a state of learning, actually. It means you're moving away from your prior and you can learn so much more now. But again, I don't want to scare you. I'm just trying to show you the process. And then we'll go through things step by step. So what we're assuming at this stage is that all the measurements that we collected they have the same status, and the three radars don't make a difference, right? Because what we're saying is that there is a vector of measurements taken at certain times of certain temperatures, right? We're not saying it was T or N or R measuring these. But we've seen that the different radars, the different measurers, they don't look the same, right? We might have some doubts about one of them, the quality of the data. So what we want to do is to tell the model that there are three different sources of measurements, and they might be slightly differently reliable. So, and again, don't get scared. I just want to show you the kind of things that you'll be able to do at the end of the course. But here what we have is we have the number of observations, the number of radars, the time and temperature, just like before. But then we also have a vector of length n, as many as the measurements, which tells us on a data point by data point who the radar is. We then have the initial temperature, which is also by radar because they are measuring the initial temperature, right? And the flame temperature. We have a vector of hot because from different measurements, we might estimate different hot constants and different sigmas, different measurement errors that the single radars are doing. And the rest is pretty much the same. We have the priors for hot and sigma. We have the vector mu, where the only thing we do is we specify that the initial temperature varies by radar and that hot might vary by radar. And then we say that the sigma might also vary by radar. We're going to make much more complex multi-level models, but we don't need to go complex for every model, right? You have a question?
Why would we stratify?
Yes, that's a very good question. You could say it is.
Because we don't believe that it can be different among three, right?
No, exactly.
Physical consciousness.
Yes. Yes. So if I wanted to go one step further, I would say we have different measurements which can lead to different estimate of hot by radar, which are sampled from the same underlying hot. So I would make an additional layer. Right? But yes, we'll get there. We'll do that. That's a very good observation. So here is a small question for you. Right? The way I've done this, and I forgot to go and fetch the markers, sorry, but is I'm feeding a vector that has the time, the temperature, and the radar. The time, the temperature, and the radar. Why don't we have instead a matrix where each column is one radar and each row is a specific time and the value inside is the temperature? Yes. So there's different ways of presenting the data, right? And a lot of people are used to metrics-like data. So now I'm feeding a vector, a long data frame, if you discuss long and wide stuff. But in a lot of these probabilistic languages, the standard format to feed this kind of data would be a matrix in which each row is a point in time and each column is a radar, and each cell is the temperature measured by that radar at that time. Yes.
I think the long format is good when you could have different number of observations. Right?
Yes, and people are not measuring things exactly at the same time.
Yeah.
So we are using, in a sense, a long format, which you're probably used to, But if you use tabular data, the reason we're not doing that is that it's much smarter to do just one vector, and we don't need to deal with missing data and the like. Good. So we can fit this. Did you do BRMS in other courses, or did you do? Okay, yes. Did you also do ULAM? You've done everything. That's fantastic. You can technically fit this model with BRMS, and I put you a slide here, and also with ULAM, but it's not fitting things very well, and I haven't explored the back stand code that BRMS generates yet, but you could look at that. Then what I do is I fit the stand code. Maybe I should mention, I have a slide later on the course notes. So online, there is a set of book chapters based on what I teach in the course that get updated usually a week or two before I teach, if I manage, where all the code that is used to do the lectures is written down, explained in text, and commented. Right? I'm not going to go through all the details of the code that is not necessary for the class, but you can always find everything in the course notes. So I fit the stand code, and I get 3 different fits for the 3 different measurements because I'm stratifying things, right? I'm saying there's different sigmas and different hots. How does it look to you? How does it look like? Is it better than before? Yes. Yes. So it's not really dealing very well with the initial temperature, but maybe that's not a too bad thing because we don't really care. What we care is its ability to define the time and the temperature at later points. Yes. We see the slowdown, right, that we didn't see before. This is helpful. Anything striking that you note? Yes, Martin? Yes. Yes. Good. And this is where modeling helps us understanding the phenomenon that we're trying to measure. What happens in this case is that I was trying to outsmart my kids, right? And so I was assuming that the baking stone has a homogeneous temperature. I thought, well, the flame is all around. Then if I measure the center of the baking stone, I'm going to have a much more reliable measurement of the temperature, right? My daughter measured the boundary between the flame and the baking stone. And it turns out that the lamp capacitor model, or the Newton's law of cooling, assumes a instantaneous transfer of heat between the flame and the body. And if you make that assumption, the border of the baking stone, which is in contact with the flame, is a much better approximation of the model than the center of the baking stone, which takes time to warm up. Does that make sense? So this is really telling us if, depending on what we want to do, we might want to measure it in different places, but given the model that we've chosen, what it really describes best is the boundary between the body and the flame, which I thought was pretty cool, and she was very proud of having had the best data. And that was the thing. Okay, then we can turn around the equation. I'm not going to go through the details of that, otherwise we're not going to cover the studio ordering, the study regulations, but we can turn the equation on its head. You can check it on the course materials. And then we can say that given the flame temperature, if we follow N or R, TR or R, we can have the exact time at which the temperature should be 400 degrees. And we can calculate it from the initial temperature and the flame temperature, go play cards, and put a timer. And now I'm hungry. Yes. So why are we even talking about this? And I think you got it, but Of course, pizza. You can always talk about pizza. Actually, my kids hate pizza these days. I just don't get it. But the idea is that even a very well established, simple to measure physical phenomenon like temperature requires careful modeling to have meaningful, interpretable latent parameters and make accurate predictions. So we learn something about heat transfer, the specific latent parameters of that oven, and we could make predictions, but we needed to actually do a lot of reflection and rely on cumulative science, that is on previous models of those phenomena. I also want to mention for the nerds among you that if you think that temperature is simple, you should go and read this amazing book called Inventing Temperature that tells of the 200-300 years of research that underwent the definition of what even temperature is and how we measure it. It's a really cool, very nerdy, but really cool history and philosophy of science book. For instance, the French people, of course, they wanted to define temperature according to the temperature of the Paris catacombs, which stays constant according to them, even in the winter, even if they didn't have thermometers that were good at that point, but of course it was fixed. And the temperature of the first day in which the snows were melting in Paris, right? So how to define even these sort of things is actually, in a sense, it's very relieving for cognitive scientists because it says, well, they seem to have their shit together, the physicists, right? They did it. They had to go through these growing pains as well. He has another book that I haven't read yet that's called How Water Became H2O, which is, again, how did we develop an understanding of molecular composition. But yes, if we want to model less graspable phenomena like memory, learning, and other cognitive processes, right, we need to, take a page from that book, and we can't just throw regressions and stuff, right? Even if we have the best design experiments, we need to think carefully about what we want to model, what is the underlying phenomenon that we're interested in, and what is the mathematical shape that relates the measurements we can do and the latent phenomena we want to describe. The course is exactly attempting to push you in that direction, slowly building up ways and tools to computationally formalize cognitive processes, explore the implication of these processes, of these models, and fit them to real data. We'll do that in 4 different modules where we repeat most of the steps in each module, so you get to learn. Repetition is the key to learning. So, why are we doing cognitive modeling? Well, the idea is that we supposedly know stuff about cognitive processes, at least you who study cognitive science, right? You had your intro to CogSci, you had decision making, you had a bunch of courses where you learned supposedly how these cognitive processes work. So we actually should use it to learn more from the experimental data instead of just using whatever regression model to put to test these ideas, right? Let's take these verbal models, formalize them, right? And see whether they actually describe the data well, where they fail, and what that tells us about theory development, right? The steps that we would need to do to improve our understanding. And yes, I'm going to skip that. And this builds and complements on your previous focus on the theories in cognitive science, which we'll learn how to formalize and develop. Focus on experimental design, because experimental design not only allows you to set up the most informative and realistic context for assessing hypotheses, but it should also be implemented in the model, right? We'll see when doing the equivalent, Bayesian equivalent of power analysis, that how many trials you have your participant do or how you choose the stimuli actually has a big impact on the power of your model to discriminate differences between, I don't know, patient groups, right? But also by running the model and simulating its behavior, you can inform experimental design, right? You can say, well, actually, it's much better to have way more participants, but only a few trials, or vice versa, if we want to do this. Or it's much better to calibrate on the individual perceptual sensibility, the stimuli that the single individuals are getting, because that changes drastically the power of our model to answer our question, right? And then statistical modeling, because your current understanding of laws of probability, of Bayesian technique, and these very early, I call it inchoative because I like fancy words, but this initial understanding of workflows and pipelines that you develop is something that we will build on and develop. Okay. So I think I'm gonna do that. I really love this passage. These again reiterates how I see models. It comes from a book called Models of the Mind. And it goes, the web-weaving spider Cyclosa octotuberculata inhabits several locations in and around Japan. About the size of a fingernail and covered in camouflaging specks of black, white, and brown, this arachnid is a crafty predator. Sitting at the hub at the hub of its expertly built web, it waits to feel vibrations in the web's thread that are caused by struggling prey. As soon as the spider senses this movement, it storms off in the direction of the signal, ready to devour its catch. Sometimes prey is more commonly found in one location on the web than others. Smart predators know to keep track of these regularities and exploit them. Certain birds, for example, will recall where food has been abundant recently and return to those areas at a later time. Cyclosa octotuberculata does something similar, but not identical. Rather than remembering the location that have fared well, that is, rather than storing those locations in its mind and letting them influence its future attention, the spider literally weaves this information into its web. In particular, it uses its legs to tug on the specific silk thread from which the prey has recently been detected, making them tighter and therefore more sensitive. The tightened thread are more sensitive to vibrations, making future prey easier to detect on them. Making these alterations to its web, Cyclosa octotuberculata offloads some of the burden of cognition to its environment. It expels its current knowledge and memory into a compact yet meaningful physical form, making a mark on the world that can guide its future actions. The interacting system of the spider and its web is smarter than the spider could hope to be on its own. This outsourcing of intellect to the environment is known as extended cognition. When a scientist, mathematician, or engineer writes down an equation, they are expanding their own mental capacity. They are offloading their knowledge of a complicated relationship onto symbols on a page. By writing these symbols down, they leave a trail of their thinking for others and for themselves in the future. Cognitive scientists hypothesize that spiders and other small animals rely on extended cognition because their brains are too limited to do all the complex mental tasks required to thrive in their environment. Well, I guess biologists would say because it's more effective to use the web than to use the brain, and it's more cost effective in terms of resources needed. We, the humans, are no different. Without tools like mathematics, our ability to think and act effectively in the world is severely limited. Mathematics makes us better in some of the same ways written language does. But mathematics goes beyond everyday language because it is a language that can do real work. Here I'm a bit skeptical. Language can also do real work, but it does a different kind of work. The mechanics of mathematics, the rules for rearranging, substituting, and expanding its symbols are not arbitrary. They are a systematic way to export the process of thinking to paper or machines. Alfred Whitehead, a revered 20th century mathematician, has been paraphrased as saying, the ultimate goal of mathematics is to eliminate any need for intelligent thought. Right? So the idea is that by developing our mathematical skills and the models, not only we do internal changes, and we have learning, but we also create a different system in which we can do science. By creating a model of theory of mind, as we will see, or categorization, and putting out there in a formalized way, we allow ourselves and others to more effectively go and modify and criticize and develop these things. And we change the way we and other things about this phenomena. Right? Language does the same thing, but with mathematics, we can be much more precise and we can have models that fail much more easily than verbal models. You probably discussed when talking about replication crisis and these sort of things that really a lot of the theory development that underwent social sciences was really something about, oh, and this data doesn't replicate that, there must be a hidden moderator, right? And then the theory was able to sort of not change and still accommodate this new piece of data. I also wanted to mention that I really like in the description of mathematicians, right, that write symbols down and says, if we take these into account seriously, we change our idea of cognition, right, from something that's just computationally internal to something that's extended. And the funny thing is that if you read the first papers by Newell, by Turing, by von Neumann on how a computer would work, they take the mathematician writing symbols on the blackboard as their starting case. And indeed, what is the Turing machine is the writing of symbols on an endless strip of paper. Right? But somehow in our cultural evolution, what happened is that the computer became a model of internal cognition when it started as a model of external cognition, which is kind of ironic and cool. But yes, again, that's one of my big defects. I always give students way too many books than they can read. But those are 4 really good books. Well, I've read 3 of them, and I'm waiting for the second one to come out on February 10th. But there are at least 3 of them really good books on how we build mathematical models of the mind, in models of the mind and what makes us smart. And Escape from Model Land is actually about weather and things, but it's about how failures of models tell us more than models working. Good. So basically, this is you before decision making. Regressions, t-tests, ANOVAs, correlations, GLMs. And here is a universe of wild exploration, fun, bespoke cognitive modeling. And one of the goals of this course is to avoid what 90% of cognitive modelers are doing, which is just finding new boxes where there's pre-existing models and you only move within these models. We'll try to think things from scratch. We'll use existing model to guide our thinking, but we'll try not to get close by them. Okay, well, I'm gonna skip this. I'm gonna say, I'm gonna skip these as well, I think, because you know why we're doing Bayesian. So how is the exam and how are we gonna get there and how it fits the goals of the course? We're gonna have a portfolio exam with 4 assignments. The first assignment, which is gonna be due on February 19th, You'll have to describe and motivate one possible verbal model about the task that we're going to play tomorrow, the matching pennies game, is solved, and provide an algorithmic formalization in R. Or I teach in R. If you're keen on doing things in Python or Julia or whatever, you can do that. Just don't expect as much support because I mostly code in R and Stan. So this is going to cover how we develop verbal models and formalize them in algorithms. The second assignment, which is going to be due on March 26th, is about building a Bayesian workflow to analyze the very same task. You have to pick two algorithms from the discussions that we've had in class. You're going to simulate and visualize data from these algorithms. So it partially overlaps with the first one. And then you will have to build and fit Stan models on that. So first you generate data as in the experiment using an R script where the parameters are decided by you in advance. And then you create a Stan model that can infer those parameters from simulated and empirical data. But we don't do empirical data yet here. Then you produce a written report of the setup and analysis. And these is going to be developing your skills in terms of how do you build the Stan models and how do you analyze data with formal models. The third assignment, which is due on April 17th, which is, I think, a week before one of the HCI reports that you'll need to do. We try to coordinate so you don't have the final load exactly at the same time. You'll have to, well, we'll discuss in class different Bayesian models of Bayesian cognition. So Bayes, not just as a way of fitting model, but actually has a model of how the brain works on a specific set of tasks. And then you will have to adjust and apply those models to a different task on social conformity. And this will teach you how to extend and change existing models to fit new experimental paradigms. And the fourth assignment, which is due on May 8th, is called the Alien Categorization Challenge, where we're going to start from an experimental task, and you'll have to build, with some guidance from me and examples in the lectures, your own model that describes those data, or that describes the interesting underlying cognitive processes that are part of the system that generates those data. Passing criteria are that you get instructions per each assignment, including a few questions to answer. They're going to appear on Brightspace. You will work and make a GitHub or GitLab or whatever version control online system you want to use repository with the code and the data. Ideally as a group, and I'm saying ideally as a group because I like to give feedback on a running base. So you submit the assignments, I take a week, and then I give feedback on your solutions. If I have one solution per each of you, it's not going to happen. If you work in groups, I actually can give feedback to everybody. It's not a requirement. It just makes my life easier. You will make a prose answer to the question with the relevant plots with a link to the repository. I want you to separate the code and report, because in my experience teaching this course is that people get really into the code and they write very crappy texts. So if we separate that, you both have to make it work, but also to try to communicate it in an effective way. And this is crucial, both because when you're going to write your master thesis or scientific articles, the communication is very important, but also because in whatever context you end up working, communicating your work is very important. If you do the work, you honestly attempt to answer every question. And of course, those that are optional, so they don't count. even with error, you can pass. So this is not a course where I'm trying to fail people. It's a course where I want to create the environment where you actually really try to learn as much as you can. What's going to happen is that usually after each assignment, I will take 10 minutes during a lecture and list general issues that I found across several assignments. That list can become a checklist. So when at the very end of the course, you have to submit the revised assignments in a block, if you tackle those issues, it's a pass. The ongoing deadlines, so the submission deadlines, are for you and for me, so I can give you feedback. But formally, what counts as the exam is only the final submission. And I don't remember the date. I haven't checked it. But you know that it's sometimes in May, right? Other questions on the exam? Okay, well, you know, you've done these kind of things in methods courses, so that's not an issue. I'm gonna skip this, but you can look it in the slides. A few years ago, I asked from people working in industry if they had some comments on what they find useful from cognitive modeling to be applied in different fields, from personalized medicine to robotics to COVID modeling to big pharma. And you can read what they said there. They all find useful things there. So here is the plan of the course. As I premeditated it now, I tend to adjust things a bit as we move along. But now it's what is cognitive modeling, why we should care. Tomorrow we're going to do a class on the matching pennies. Next week, we're going to discuss going from verbal to formal models. In week 3, we're going to start working in STAN, turning your formal models into STAN models. Then we're going to introduce the notion of Bayesian workflow, that is a systematic set of practices to check and validate your model even before you look at empirical data. Then we're going to go into multi-level modeling and into model comparisons. And here we wrap up assignment 2. It's a bit of a long haul, but that's because we need to have several pieces in place, and I want to go with the pace that you need to solve all your issues and doubts, not all your issues. I can solve some of your Bayesian questions, not all your issues. On week 8, we're going to have a guest lecture by Melina Weiler, who's a former CogSci student, who's going to be talking about the cognitive modeling of effort and reward, basically a fancy version of a reinforcement learning model. And then after Easter, we're going to shift the topic and say, well, now so far we use based as a way to fit models, but what if we take it seriously as a model of how the mind works? And so we're going to see information integration as a model of cognition, which we then going to bring up to the next week. And we're going to use these model, in particular naive and weighted Bayes, first to simulate new data and then to analyze empirical data. And here we will wrap up assignment 3. I should also note that a lot of the work on the assignments is structured to happen in classes, because that means that you have me to ask questions. It's not going to be enough to just work during classes, but during the classes, we dedicate a lot of time to the assignments. And then there's the last block, week 11 to 13, which is on categorization models. Good. Lecture, classes, and readings. So for most of the lectures, there are readings listed on Brightspace. The way I conceive readings is that as I teach a lecture, I'm going to have to take a specific path and tell you the things that are relevant for that line of argument. But that and avoidably cannot cover the whole field. So the readings are a way of giving you the bigger context, right? So you're not going to need them in order to understand the lecture, but it can give you more depth to ask questions if you read them before the lecture, and it can give you more depth after the lecture if you want to go and check some things. But what I expect you is to use the bulk of your time that you use on this course working on the assignments throughout the semester. The lecture will present modeling techniques and or models with discussion. Well, readings are not necessary, but helpful for discussion, and lecture will be recorded and shared. The course note present all the code used for the lectures and sometimes more. There's an address here. Right now, there's the first 3 or 4 chapters up, but as I revise them, I'll put more. If you have comments on how to improve them, they're very welcome because I use them every year for teaching. Classes are about working in groups through the portfolio assignments, mostly following up on what we discussed during lectures. It's very, very important for everybody to code, right? So group work is very good. I think that's the way you learn best, but don't offload coding to only a subset of the group. It doesn't work to record classes because it's mostly group work. I tried 1 year, it was crap, so didn't do that anymore. And this is a course for adult learners, right? So I trust you to be very motivated in learning these techniques, in asking questions, and I'll try to make your life as productive and easy as possible from that assumption. Good. As I was saying, being confused is good. This is a quote from, I think it was no, it's actually Blue Sky now. If you are confused, it's only because you're trying to understand. It's a quote from Richard McCarthy's book, which you covered in Methods 4, right? And where he comments, I say this a lot because I'm also confused quite often. So if you feel yourself confused, you're in good company, right? So ask questions. There's no stupid questions. Ask in class, send me emails, and there is an anonymous Google Doc, which I linked on Brightspace and sent you a mail about, I think, where you can just write whatever question you want, and I try to regularly check it and answer questions there. The good thing is that it's open 24/7, and that you don't need to disclose your UR if you feel that the question is too basic or whatever. But no question is too basic. I've also experienced that in the last 2-3 years, there's been a decline in the use in the Google Doc, probably because people can ask questions to language models. But I'm not going to force you to use it, but it's actually a resource for everybody. You ask your question, you get an answer, and everybody can read it. So it's not a bad idea to use it. We don't care. So uCloud. Usually, I try to want to run things on my computer till I'm 100% sure that things work. And that's where I didn't base this course on uCloud, but some of the models might take quite some time to run. So there is a course set up on uCloud, and you're highly recommended to use it once you know that things are working on your computer. You'll have to remember that uCloud doesn't have command stand. So you might want to have a short script that installs all the things that you are going to need before you do anything. And don't just copy and paste it as I did it at the beginning at the top of every script, because then I mess things up. Just have a separate file that you always run. I think I shared a simple version of that with Johanne, and she can share it further if you need. Generative AI. So we're slowly moving the education towards generative AI-free exam forms and trying to keep things as generative AI-free as possible because it's part of the learning process. But I can neither force you to use generative AI nor stop you from using it at this point. So what I just want to share is a couple of positive ways that I found of using it when I get stuck with things, which might inspire you. The first one is that before I asked it to write up something, I actually think through and provide elaborate unit tests as part of the prompt. What is a unit test is you define a scenario where you already know the correct answer. And yes, because then you learn to think through the model. There is a very good textbook called Better Code, Better Science, which details how to do these sort of things. If you get whatever, Gemini, Claude, whatever, to generate your code, before you actually run it, explain it line by line to your group mates. Because then you actually often find bugs, but also understand what you're doing. Third is don't ask it to write a full script. Ask small things, right? Get it to generate code for the things that you know already, and then you can get it to increase the complexity, right? Again, this is not telling you you should use generative AI, but I'm just saying, if you're going to use it, these are good ways of making you in charge of the process and understanding things. And use version control, GitLab, because it's gonna fuck up your scripts so many times. Like I often use it. Oh, I want to change the style in, the 120 plots of these course notes. I don't want to have to do it manually. So please only change the code in the plots, and it changes random shit. Yes. Few additional resources, more books. You're lucky not to have had me like in social and cultural dynamics and like, because you would have had like 5 books every week. A few online materials, other people's courses that are relevant to this course. And do you have questions? Yes. So if you're working in groups, just send me an email. I'm old school, yes. And then for the exam, it's Wiseflow, whatever it's called, yes.
You're saying if in working groups, I thought it was required.
It's not required, but I highly recommend it. Yeah, you can do all the assignments on your own if you want.
Exam, it's like you individually hand it in as your own course, or do you have to
I
put like initials for who did what?
Yes. So it's an exam without censor, so it's me, and I've followed you throughout all the assignments. So in a sense, I've had people who submitted individually their group work with all the initials. I've had people submitting the group work as a group with all the initials. As long as you mark the initial, which is the formal requirement, even if you and her submit the same thing, it's not plagiarism because you're saying this is a group and here are the people parts of the group in the document.
Same thing.
Yeah.
Just have to make it clear that it's not plagiarism, it's a group.
Exactly. And people change groups. That's also fine. It's before every assignment, you just put the list of members of that group. Yes. I'm done at 1 minute before. Yes. So, yes, Martin? Does it have to be STEM? Well, I'm going to teach 10. We've had our previous experience where you did it in PyMC, and that's absolutely fine. If you get stuck in some rabbit hole with PyMC, I probably cannot help. But it's more likely that I would get stuck than you would get stuck. So in PyMC, yes. Good. Other questions? Then this has been a pleasure. I'll see you tomorrow. And before I leave you, as I sent you as an email, there's somebody who wants to ask you if you want to be part of an experiment. And it's absolutely unconnected with the course. There's no pressure for you to participate. So it's just she's presenting the study and then you decide.
Good. You took care of all the ethics.
Yes.